Good morning, everyone. My name is Michael Gammon from the University of Manitoba, and today I'm going to be presenting our research on limbo, which is about the real-time comparison and visualization of lower limb motions in humans. So we know that in the internet age, online tutorials, which are either text, picture, or video-based, have made the barrier to entry to many traditionally difficult fields lower than ever. So picking up a new skill, whether that means learning a musical instrument, advanced sports techniques, or aerobic routines, is made simpler with such references while avoiding the high monetary cost of a private teacher. And while this is clearly a positive thing, most of these methods of remote or independent learning are not yet comparable to working side by side with an expert in the field, particularly when you're learning low-level concepts. This is likely due to difficulty quantifying the similarity between a beginner's attempt at what they're trying to do and the source that they're receiving the information from. And this can lead to skill acquisition taking longer than is actually necessary. So in order to further accelerate low-cost and accessible training, some advances in virtual learning and coaching technologies are desirable. Ideally, such technologies should not only provide a reference to learn from, but also a feedback method for automatically quantifying performance differences. So it's even been shown in some research that VR training, which highlights such differences, can be more effective than training from a human expert. In doing this, though, the main challenge in creating a virtual coach that can compare two sets of motions in a meaningful way stems from the fact that, in general, temporal media comparison is a complex and challenging task. So what is spatiotemporal media? To put it simply, it's any piece of media that has information encoded both over space and time. So for instance, a photograph is simply spatial media since it only exists in one instant in time. On the other hand, something like a video has the two spatial components of a photograph along with an additional time component. In her 2017 paper, betaCube suggested that visual temporal media, such as, in our case, animated joint angle data, can be uniquely difficult to compare since the relationship with respect to time is usually equally as important as the relationship between the two or more media instances. She argues that visual design for such comparison is almost non-existent at the current time. And in most cases, people rely on their memory to make the comparison for such tasks, but this typically results in the loss of useful information. And there are many different approaches that are typically used for comparing temporal media, but they all have drawbacks to their use, particularly for real-time comparison. One of the major complications is what's called content alignment, when the media instances are meant to be played in parallel. The portions of media to be played back simultaneously have to share some similarities that are conductive to comparison. So you can consider maybe two videos of two different people performing a golf swing, for instance. The duration of the swing is likely different in each video, and not in a way that is smoothly scalable to match the initial video by stretching the file. So one video may have a slower backswing, but a faster forward swing. How is it possible for an algorithm to draw comparisons between the two videos without some kind of alignment? And it's actually not even always clear what content alignment means for media where the structure and duration are different. Should one piece of media be the master while the other jumps and varies playback speed? And what about real-time comparison to a piece of pre-recorded media? In general, these questions don't really have an answer, or if they do, the answers are unclear. So in her paper that I was discussing previously, betaCube argues that one proposed solution could be to remove the temporal component altogether and effectively turning a video into a series of keyframes. So perhaps notable key points could be the starting position, the furthest point of the backswing, contact with the ball, and the end of the follow-through. Such comparisons between a set number of keyframes selected from each piece of media drastically reduce complexity, but there is a trade-off with the amount of information that is available. One research group actually attempted to do this in their 2012 paper called SuperMirror, where they visualized the comparison of human limb data from ballet dancers using the juxtaposition of an animated stick figure with real-time skeleton tracking data from a Microsoft Kinect. So this application is meant for the coaching of ballet poses. When the pose for a given limb was correct within some accuracy threshold set by the researchers, it would change color on screen. And the group also visualized the real-time joint angles relative to the target joint angles with using the wheels that you can see on the left there. For static poses, this visualization method is quite intuitive, although it does not extend well to dynamic motions. In future iterations of the system, they plan to define each step in a dynamic motion as a series of static poses to iterate through. Unfortunately, though, this plan is not really generalizable to a motion like a soccer kick, where the smooth temporal component of a kick makes it challenging to observe the desired motion while also precisely trying to follow it at the same time. Another approach for dynamic motion comparison was presented by Weir and colleagues with betaCube, This apparatus enables many different kinds of movement visualizations for rock climbers. One such visualization involves recording and reprojection of an expert climber's run back onto the wall. And this can either be watched from the ground, raced against, or mimicked in real time, which they refer to as shadow climbing. So this gives detailed, repeatable information about the ground truth run, but it doesn't directly draw comparisons to the user's movements. Alternatively, the apparatus can also track which holds were used in succession by the expert and highlight them via the projection markers around the next holds in the climb, which you can see on screen now. This ensures that the user follows the ground truth path closely, but does not actually give feedback on the nuanced joint movement between holds, which is the key to becoming a strong climber. So in previous work, the tracking methods for motion comparison typically depend on capturing X, Y, Z positions of specific features in the local Cartesian coordinate system and then drawing comparisons between them. In our literature review, we have seen examples of this using simple RGB video capture, where pixel positions are compared, as well as more accurate Vicon and cave-based systems. And such systems have two inherent disadvantages. First, the capture methods are inconvenient and non-portable. And second, the use of Cartesian position as a means of comparison makes it difficult to compare motions from people of different heights and weights without lots of editing to the raw capture files. So you can think, for instance, a similarly performed motion from both an adult and a child will lead to very different positions of the limbs in XYZ space. So some of these problems were solved with SuperMirror, like we talked about, by using joint angles rather than position, although it's still necessary for users to stay within the field of view of the Kinect. This makes the solution impractical for anything gait related or anything that is more naturally performed outdoors or in public. So with these motivations in mind, we introduced our technology Limbo, a novel solution for the real-time comparison and coaching of lower limb motion in humans. So Limbo in its current form is presented as an Android application, which is designed to act like a virtual coach for sports activities primarily involving the lower body. With this application, we aim to find a way to quantify the similarity between a user's attempt at a given motion and a ground truth input for that same motion in real time. We also automatically provide feedback as to where improvement is needed. The application works by breaking up a ground truth lower limb motion into a series of keyframes, which are represented by the collectible orb objects you can see on screen. These are sequentially collected by the user's foot in order to increase their score. This effectively simplifies the temporal component of the comparison, as was suggested by Theoretopacule. A perfect replication of the reference motion will result in the destruction of all on-screen orbs and a perfect score of 100. Otherwise, the remaining orbs give feedback to the user as to where improvement may be necessary. So since our basis for lower limb comparison is entirely orientation-based, we obtain a full description of a leg through knowledge of the orientation of each of the three leg segments, being the thigh, shank, and the foot. This is done by strapping an IMU sensor onto each of these leg segments and using the onboard sensor fusion algorithm to stream quaternions or orientation data to an Android smartphone in real time. For the purpose of this study, we only compared the motion of one leg at a time, so using 3 sensors total, although the application is set up so that it can be extended to a total of 7 sensors. We chose the sensors for their portability, convenience, and relatively affordable price, which makes them ideal for use outside of the lab and also makes them an attractive option for in-home rehab applications. So you can see on screen here, this is an example of a user controlling the application using their leg with an IMU strapped to each leg segment. And the on-screen avatar follows while they move. So in order to compare two sets of motions, it's first necessary to collect a ground truth data set to serve as the basis for comparison. So in order to do this, an expert user wears 3 sensors on their leg and performs the desired motion with the capture mode running on the app. While this happens, the XYZ positions of the 3D model's toe are written to a file in every frame. And this position is directly a function of the joint angles of the hip, knee, and ankle, and it's purposely independent of the position of the real user's foot or leg size. So when the position data is written to file, in general, it's messy and has uneven spacing. And for this reason, it's necessary to apply a runtime filtering technique to evenly place data points along the desired path. So this way, when the user tries to compare their motion to the ground truth, a percentage of matching data points will actually serve as a meaningful scoring system. So in order to do this, we used a direction vector-based approach to smooth the pathway generated by the data points from the sensors. With this approach, a linear interpolation of the pathway between the data points was generated. You can see on screen here on the left is the raw data. So there are orbs all kind of clustered near the starting point, and they're unevenly spaced at the end. And then after we run our algorithm, it looks like you can see on the right there. As was mentioned in the previous slides, the user then guides the avatar's toe through the on-screen orbs and receives a score of 100 to represent how closely they mirror the desired motion. Since we chose to break the temporal component of the comparison down into keyframes, the only time dependence that remains is the order in which the user collects the orbs, as well as the direction of motion. So the direction of motion is handled through a color coding system. The orbs are either displayed in a red color, which is directionally ambiguous, or gold or blue to represent forwards and backwards motion, respectively. The orbs are only supposed to be able to be collected if the direction of motion is as intended. And the reason for this is that some motions include both a forwards and backwards component that can cross paths, and it's not desirable for the user to accidentally start collecting orbs from the wrong part of the motion. And then also, since the visualization in its current form is just presented on the 2D smartphone screen, we implemented a change camera button just so that the user can see the pathway from multiple angles, which is necessary for accurate replication. This can be done at any time, and the user can perform the orb collection in whichever view is preferable. Now, in order to evaluate our application, a within-design study was conducted where 16 local university students participated to explore the efficacy and the user experience of our visualization approach in Limbo. So the participants used Limbo to help them replicate two different lower limb motions, both a soccer kick and a circular leg sweep motion. We also constructed a video comparison control scenario where we recorded the ground truth data sets for Limbo. When we recorded the ground truth data sets for Limbo, we took a video recording of the motion from the front and side angles to be comparable to the two camera angles in Limbo. Using these same camera angles, we were also able to live stream the user's own motions to a phone so they could watch their movements in real time. When participants attempted to replicate the motions using the video comparison method, they would watch the ground truth video from both angles and then watch their own live stream in order to match the motion as closely as possible. This made our control scenario as similar as possible to our app, just without the feedback of the collectible orbs. While the video control scenario was completed, we also had our app running in the background so that the orb objects would still be collected without the user's knowledge. This provided us a basis for quantitative accuracy comparison. So here on screen, you can see the angles of the live stream for the video comparison, which streamed to the phone in the user's hand. The ground truth videos were also recorded from these same angles. And we wanted to see how the comparison methods differed between simple tasks and difficult tasks. So we purposely made one harder than the other, namely the soccer kick was requiring a much larger range of motion. And we also made sure to randomly assign task orders in order to minimize order and learning effects. Overall, our study confirmed Limbo's stronger efficacy compared to the video comparison method, which shows us that Limbo has great potential as a practice method, as the user is more likely to be practicing the motion similarly to how the ground truth was actually inputted. The study also confirmed that the majority of participants preferred Limbo as a learning method, found it to be better for understanding the reference motions, and made it easier to focus on learning the task. Additionally, users noted that perceived difficulty was actually higher when using Limbo than when using the video comparison method for both of the tasks. Besides a lack of familiarity with the new technology, this is likely due to the fact that Limbo is actually less forgiving of deviations from the ground truth dataset, whereas with the video method, users wouldn't receive any feedback on such deviations. So this leads to the feeling of perceived difficulty in replicating the motion. And while it might seem kind of counterintuitive, this perceived difficulty might have actually been a key to the positive outcome. In fact, for both tasks, the actual scores were higher when using Limbo. So the perceived challenge will lead to a user being more careful and deliberate with their motions and learning the motion more accurately in the long run. In the open-ended questionnaire, many reported liking the fact that they could see concrete evidence of where they performed poorly, making the motions easier to learn, even if they were actually performing them, or even if actually performing the motion was more challenging for them. Similarly, for the more challenging task, users reported feeling more physical awkwardness using Limbo than the video comparison method. And for the less challenging task, this difference wasn't as significant. So this could also be attributed to a similar reason as described previously. Since the app is less forgiving, it's more likely to push a user to try harder to fully replicate the difficult motions, even to the point of feeling slightly physically uncomfortable if that's what the proper replication of the motion requires for that user. And across movements, participants reported more pleasant feelings associated with using Limbo, which was found to be an indicator for future use of the technology. One of our main concerns with the current implementation of Limbo stems from the typical performance gap between an expert and a beginner. So performing a karate kick even remotely similar to a black belt might be an unrealistic goal for an average user. And for that reason, the feedback provided by the lack of orbs collected might only have a little bit of use in these cases. So in future versions, we intend to implement motion interpolation between a user's best attempt and the expert's motion based on the work done in Interposer. This way we could provide an intermediate motion path for the beginner to replicate that is closer to the expert's motion while still being a realistic goal. In future iterations of this app, we would also like to explore being a little more concerned with the minutiae of movements, namely introducing a further velocity dependence and maybe being more precise about orientation. So in its current form, since the orbs are only placed over the path that the model's toe follows, there are multiple states that the leg could occupy to collect a given orb. Adding additional orbs to collect on the knee joint and potentially even the ankle joint as well removes this ambiguity. Although it could lead to a cluttered looking visualization and maybe be confusing for the user. So a little bit more explanation here or exploration here on visualization methods is necessary for something this specific. Another obvious extension is to add movements that include both legs. We are also interested in integrating Limbo into a virtual or augmented reality interface. So instead of attempting to interpret the three-dimensional data through changes in camera angle on a two-dimensional screen, the user would be able to exist in the same space as these orbs for a more immersive experience. It would also be interesting to test the psychological effects on learning when being immersed in the motion visualization. I know that studies on the level of experienced immersion in VR when controllable virtual legs are present is not largely non-existent outside of patients using virtual legs for helping to treat phantom limb pain. And finally, it's much more affordable for a patient in rehab that has severe mobility issues to buy a pair of sensors or a few sensors to pair with their smartphone, as opposed to paying a physiotherapist for in-home visits. So in future work, we look for ways to make this process entirely remote. The therapist could upload new motions to the cloud and track the patient's progress without actually ever having to be in the same room. Thanks, and I can take questions if you guys have any.
Thank you very much for your presentation, Michael. Yeah, dear audience, please kindly forward your questions to Anna. There is one question for you, Michael. How far is the project from extension into virtual and augmented reality?
It's hard to say. So we haven't actually started implementing the AR or VR portions yet, but we built the app in Unity, and everything else would work pretty much the same. So I think that's probably a next step, and in the coming month or two, we're going to start implementing that, and yeah, hopefully it goes quickly.
Yeah, thank you for your answer. Then one more question. What's your team measured with the IMU sensor, where rather large body movements, but do you think you can measure much more sophisticated movements like finger or toe movements?
That's an interesting question, actually. So the IMUs are pretty accurate. So just sticking to leg motions for a sec, like one of the things we're doing is looking at physiotherapy, which do involve much more subtle movements, just small movements of the leg up and down, exercises for patients with mobility issues. And for those types of exercises, they seem to work quite well still, even on those smaller scales. But when it comes to hand and finger movements, it's a little bit more finicky. It's funny, actually. Another project I'm working on right now, we're using these same IMUs, and we've attempted to use them as a thumb controller for detecting touches on the hand. And they work, but maybe not. The implementation isn't quite as good as we'd want it to be. So they are very accurate, though. So I think it's just a matter of how good the implementation is.
Yeah, thank you for your answer. If no more questions, then we'll move on to the next presenter. Thank you very much, Michael. It was a wonderful presentation.
Thanks.